So, welcome everyone. So this talk is also very academical, just like the previous talk. Just let me first introduce myself. So my name is Slaski. This is the correct spelling of my last name. I work in Spartez. Spartez is hiring. But this talk is not really related to anything I do at work. So many years before I joined Spartez, I was studying in Warsaw University, and then I was on some internship in university in Gothenburg. And those are places that are very much, well, maybe not the whole places are focused on functional programming, but there are very strong groups studying functional programming, and particularly type theory and proof assistance. So once I took a class in Coq, and today I'm going to squeeze the semester of lectures into one short talk. So I'm going to speak very fast, but if I'm going too fast, then please interrupt me, ask questions. There are many proof assistants. I'll talk about Coq because I know something about Coq. The others are probably very much different, but I have no clue about them. Let's start. First of all, we are in the world of intuitionistic logic. Logika intuitionistyczna. This logic is also known as constructive logic, and it's very much different from the classical logic that everybody, I guess, pretty much everybody had a class once upon a time. So it has the same language, but it has different axioms. Actually, there's only slight difference in axioms. So those are the typical axioms that you may or may not remember from school, implication. This is called modus ponens. Yes. So this is conjunction axiom, and this is alternative axiom, and this is false axiom. False. Yeah, this is false. This is simple. False implies everything. And probably you may remember that there is also an axiom stating that A or not A for every A. And that's very natural to have this axiom. Like you say, either it's raining now or it's not raining. There's no other option. And this is actually called law of excluded middle. There's no other option, no third way. But in intuitionistic logic, the guy who came up with the idea, it was Professor Brouwer from Amsterdam. It was early 20th century. He found something wrong about this axiom and decided to get rid of it. And what is really wrong about it? That you prove some property, some theorem, and imagine you use this axiom, but you don't really know, is it A or not A? And actually that was the case with his famous theorem, fixed point theorem of Brouwer, by Brouwer. The proof was not constructive because he used this excluded middle law, and as opposed to other fixed point theorem by Banach, which is very famous, and the theory by Banach gives you exact way to find this fixed point of some transformation of some spaces, doesn't matter. And the Brouwer theorem gives, I think it's a stronger theorem, it's like in a way it's better, but doesn't give you way to find the fixed point. And Brouwer was at some point very frustrated with this problem that he knows that he can prove that the fixed point exists, but have no clue how to find it. And he came up with this entirely new approach to mathematical logic that's have some like practical and philosophical implications. He wants constructive mathematics, constructive logic, and so he just erased this axiom and looked what he can do with all the rest. So Brouwer and his student Hating came up with some new interpretation of mathematics. And this is called Brouwer-Hating-Kolmogorov interpretation. But Kolmogorov, I think he's a Russian guy. He didn't live in Amsterdam, so I don't know exactly how come they work together. But that's the name of this interpretation. So they say, okay, let's say that proof of A and B is a pair. It's proof of A and proof of B. But that makes sense. Huh? So proof of alternative A or B is a pair. It's also a pair, but like first element of this pair is a flag. It's either 0 if you're proving A, or 1 if you're proving B. And the second element is the actual proof, like respectively of A or B. And this way you don't have the problem with excluded middle. If you have a proof of alternative, you always have a proof of either the left side or the right side. Now, proof of implication is a function that takes proof of A and creates proof of B. Proof is a function, okay? So maybe you'll see that this somehow resembles some programming, maybe some functional programming. This proof is a function, like everything is a function. Maybe it rings a bell. So there's also such interpretation for existential quantifier and universal quantifier, and also for false. So not A means that A implies false, and there's no proof for false. False has no proof. Yeah. So if you think this somehow resembles programming, then this correspondence is attributed to Cade and Hort, these two American logicians. Actually, Haskell Carey, Haskell is his first name. He's like, maybe you never heard of them, but maybe you heard of the language Haskell. So Haskell is also named after this guy, Haskell Carey. And Howard was I think was his student. So now look at the correspondence. So in a way, axiom somehow corresponds to a variable. What is introduction rule in logic is a constructor. What is elimination rule is a destructor, or normally we call destructor pattern matching, because we can oh, by the way, how many of you know Haskell or Occam? Yeah, quite a few of you. So you know what I mean, like when you have algebraic data type and you have a constructor and destructor. So this is the kind of pattern matching I'm referring. So the probability, the property of probability of every proposition, if you have a proof, you say that this proposition have property of probability, and it's a theorem, in other words. So in programming, the same problem is type inhabitation problem. So you have some type, and you're thinking, is it possible to write a function for such a type? And sometimes, like, you search in some API documentation how to construct this type. So basically, it's kind of proving theorem in a way you can think about it such a way. So this categorized correspondence, like in Polish we say isomorphism categorialna, but it's not like isomorphism in a strict way, because it's not an object, it's not a formal object, it's rather new way of thinking about programming and mathematics. Okay, so that's kind of the theory behind Coq. Like I'm giving like very high-level overview, so trying not to go into details. Just instead, I will in a few minutes show you this Coq IDE and how we can play with it, and I will try to convince you that it can be fun. Yeah, but just a few more slides before we go into some live coding exercise. So as I mentioned, there are many proof assistants, and some of them that are worth mentioning are Coq, of course. So Coq is developed in France. INRIA is kind of like Academy of Science, National Research Institute, something. Agda is another famous one. So Agda is actually very closely related to Haskell, and it's developed in Gothenburg. F-star is developed in Microsoft. NuPRL, I think this one is really big, is developed in Cornell University, and Mizar is developed in Białystok University. And Mizar I never used that, but I know that it has really exhaustive library of theorems proven with Mizar, probably the largest of all of them. So like, so I guess like Warsaw and Białystok are the two places in Poland very active on the fields of proof assistance. However, like Białystok, like in Warsaw, it's a kind of like functional programming. It's this type theory, and Mizar is totally different. It has nothing to do with this categorical isomorphism. It's a totally different approach, as far as I know. Okay, so the Coq itself. So it's developed since 1989, and there are like 3 inspirations for the name. So first of all, the word coq means rooster, cogut, in French. The second inspiration is calculus of construction, and like abbreviation is Coq also. And calculus of construction is the exact theory behind Coq. And also it's first 3 letters of Thierry Coquelin, that was the head of this research group in INRIA when they developed Coq. Coq was awarded with ACM Software System Award 4 years ago. It's written in OCaml. OCaml is this programming language also developed in INRIA, actually. So the language of Coq is called Galena, but there's also another language, LTAC, that is used for defining tactics. So I will show you in a very few minutes what are tactics. But just now I'm explaining that tactics are also like you can write a custom tactic. And there's a feature of exporting proofs into programming languages, OCaml and Haskell. And so what is Galena? What is this language? So first of all, it's not Turing complete. I guess like most of programming languages use are Turing complete, and this one is not, and this is on purpose. This is because we want programs always to terminate. And why is that? I just prepared this little snippet of Java code to explain what is, like why Java cannot be considered a proof assistant. Because that's a perfectly valid Java code. This is function, this type of this function is for every alpha, alpha. So that's false, in other words, for every alpha, alpha. You don't want such a program to be you don't want this type to be inhabited, because this means that that false is provable. So Java is no good for, and any other language that we use for programming is actually no good for this purpose. It's tremendous importance to understand this difference. So programs in Galena always terminate, but anyway, you can express recursion, you can express a lot in this language. Just you must be very careful. So two more things. There is a hierarchy in Coq. So what is the type of 1? Well, 1 is a natural number, so we call this nat. So what is the type of nat? So natural numbers are set. So the type of nat is a set. So what is the type of set, you may ask? Well, it's type. And what is type of type is also type, but for consistency, it's a different type. So there is just infinite hierarchy of these types: type 1, type 2, type 3, etc., etc. And there is also prop. Prop is type of propositions, and it's kind of on the side. And why is that? There's actually important reason behind that I'm just going to signalize very briefly. So these types are predicative, and prop is impredicative. So what does it mean? The notion of predicativism was introduced by Bertrand Russell in 1907, and that was his answer to the paradox he came up once. So this is famous Russell paradox. He tried to, he considered a set of all sets which do not contain themselves. Zbiorów wszystkich zbiorów, które nie są swoimi elementami. So that this paradox was a shock when Russell came up with it, because the foundation of mathematics was basically broken, and mathematicians at the first place didn't have answer to that. It seemed that math is fundamentally inconsistent, and they were looking for various answers, and Russell came up with solution that this paradox exploit the impredicativism. And if we forbid impredicative definitions, then everything is safe and sound. But there are also other answers, and normally we nowadays use, when you think about set theory, it's ZFC, Zermelo-Frankel theory. They have Zermelo and Frankel, they provide a different answer to that problem, but Russell came up with this predicativism ideology, and he wrote his famous book Principia Mathematica. So he basically translated the whole mathematics onto this predicative type theory with infinite hierarchy of types, but somehow he didn't catch up. Only Russell himself and Whitehead used that theory, pretty much no one else. And why is that? Probably because actually mathematical analysis, which is a very important branch of mathematics, mathematical analysis is fundamentally impredicative. for example, greatest lower bound definition is in Predicative if it iterates over. Exactly, there's no precise definition. Like people disagree what is Predicative, what is Predicative, what is impredicative. But the rough idea is that a definition should not iterate or quantify over a set that contains the object being defined. So exactly, this is exactly such quantifying, and greatest lower bound is also quantifying over the set that contains greatest lower bound. Greatest lower bound is correspond. Okay, so that's the end of these slides, and we can move to live coding exercise. Just some links. So this is link to Coq, and this is link to examples that I will show in a moment. And and one more word about Coq itself. So yeah, this is Coq. Examples. So Coq has is like this nice IDE. It also has some command line tool. Personally, I always use this IDE, so that's what I'm going to show you. And how you interact with this? Maybe I sit down and try to operate.
Right, because this Scala.
Maybe move the Scala.
Okay, that's better.
So this window is divided into 3 parts. First part is kind of our buffer. And here we write some definitions and some proofs. This part of window, it's a proof console. So state of our proof will be displayed here. And this is a side console, and we can check. We can do some checks. For example, we can check what is set. Set is a type. So, and here we have these buttons to progress our proofs. So first of all, I have these very, very simple examples just to show you the syntax of Coq. So first, I'm going to define natural numbers, and as it happens with functional programming, I just define 2 constructors to define the set. So this is a correct definition. I mean, this green color. Oh, it's not green on this. It's much more green on my display. So if I press a button and you see the green color progressing, then it's correct. If I write some nonsense, and then probably we'll see some error. So this is the way you interact with Coq. So first, let's define some numbers, 0 and 1, and now define predecessor. So, by the way, you're familiar with this definition. So this capital O stands for 0, and capital S stands for the successor. So now we define the predecessor operation. So for 0 it's 0, and for successor of x it's x. So successor is x plus 1, so predecessor is just x. Yeah. So now let's define plus addition. So we define this is a recursive, of course. Plus is a recursive function, so we use this fixed point keyword. So I know, should I explain what the moral meaning of this definition? No, I guess I should explain. Oh, okay. So we are adding n and m, and we are pattern matching on the first argument. If it's 0, then the result is just the second argument. Otherwise, we use recursion to compute. So this pattern matching says that n is successor of some p. So we say that result would be successor of m, the original m, and p that is n minus 1. So because we are pattern matching, then probably we use recursion, but we also use pattern matching. So we can guess, and the Coq has checked that this function terminates, and it's a legal. In this way, it's a legal function in Coq.
What's the difference between definition and fixed point?
So definition cannot be recursive. And there's another keyword, compute, and we can try if this computation is correct. So it's 1 plus 2, and indeed 1 plus 2 is 3. It's a very good definition of addition. So now we have some other fixed points, some silly fixed point, and this definition. So this function goes into infinite recursion because like n is some successor, and we put the same s of p in recursive call, and it should not compile, and it doesn't compile. Coq says that it cannot guess decreasing argument. So if that was actually a valid fixed point, we could probably give some hint or some proof that it's terminating, but this is not, so we just delete it, and we don't need it. And now I show some simple theorem how to prove it. So let's prove that for all natural numbers m and n, m plus 1 plus n is m plus n plus 1. So I guess it's very intuitive that this is true, but probably like if we were in school, you would say this is trivial, but we are not in school, we are in front of Coq, so we must do a proper proof. And this is how you interact with Coq. So there is you have some goal, and you have some tactics. These terms I'm using here are tactics. There is plenty of tactics, and like, to use Coq fluently, you must probably learn many of them, which I didn't, but I know enough to prove this simple theorem. So first of all, this goal is like too long to analyze it, at least for me. So I use tactic intros. And now I don't have this for all quantifier, but instead I have in my space, I have two new variables or hypotheses, assumptions, whatever. Yeah, I think this like above are assumptions. So my assumptions are that m is natural number and n is natural number, and now we can prove something. And like, if I may, there is like, for me that's a lot of fun to use Coq, and I look at this as kind of role-playing game. So this is my quest, and this is my inventory. And when you have a quest, for example, to kill a dragon, you usually split it into smaller quests. First, find a ship, then stuff it with some sulfur, then deliver the ship to the front of the cavern, and then probably the dragon will be killed. So in Coq we do the same. We collect some inventory like sulfur and whatever, and we split our quests into simpler and simpler quests as long as we can prove it. So first of all, let's simplify this a little bit. So this tactic simple makes some useful. It basically unfolds the definition to make some useful simplification. And now we have a problem. Now I don't know how to prove it. So when I don't know, I try with induction. And we have induction tactic. So induction tactic basically split our problem into the base case. So we prove for m equals 0, and then we will prove the step. So first the base case. So the base case is simple, so we just use tactic simple. And now it's trivial, so we use tactic trivial. Okay, done. Now the hard part, this is the step. So we know we have inductive hypothesis for m, and now we have to prove the same for successor of m, for m plus 1. So first of all, unfold the definition. So now let's use the inductive hypothesis. So actually we see that this side of equation is also here. So, and this side is also here. So let's use rewrite tactic because it's equality, so we can rewrite our goal. Okay, so it was the right part is substituted. So now it's trivial, so let's use trivial tactic. No more subgoals, we're done. And how much time I have? Okay, so I skip the other simple example and I will go to the more advanced example. So now I'm going to prove that every number is either odd or even. So this definition expresses the idea of being either odd or even. Yeah, for the given natural number n, we proving that it's either n is m plus m, either exists that there exists some m that either n is m plus m or m plus 1. So I hope you agree that this is pretty much either odd or even. When I prove it, I will try to extract this proof to Haskell and show you how cool it is. So the problem with this proof is that if you use these induction tactics, it's a bit difficult. I didn't figure out how to prove this with induction tactics, so I defined some more fancy induction. This is, I call this double induction, but it's not a good name. It's actually my private induction. And this induction has two base steps for 0 and for 1, and then it proves this hypothesis for it takes proof for p of n and p of n plus 1, and then proofs for p of n plus 2. And p is the property induction should prove. Is it understandable? Okay. So let's go. So first of all, I realized that I need even stronger. I need to prove even stronger theorem. So it's a slight modification on the end. I want to conclude that this is for p of n and also for p of n plus 1. So I create a new goal in my proof. So now I have two goals and I don't have any assumptions. So let's make some assumptions. So now I consumed everything that was before, like this is everything that was before the last implication and this n that was under quantifier, they are hypotheses, and we are left only with this conjunction. So do you, I don't know, are you with me? Do you think it's a legal, it's a valid proof? I hope you do, because it is. Okay, so again, I don't know how to prove it, so I use induction. I use induction to prove induction. So first of all, I must prove it for base case, but actually both sides of my conjunction are my hypotheses. So I just split the conjunction, simplify, and use assumptions. And if it's like, I can use semicolon to combine tactics. Okay, so first goal is done. Now I have this inductive hypothesis and I'm proving step. So step is again conjunction. So like I'm going to prove it one by one. So I have two goals and I focus on the first one. So how I prove it? I'm using, I need this inductive hypothesis because that's the only good weapon against this dragon is my inductive hypothesis. So I distract this. In other words, I do pattern matching on this inductive hypothesis. And what is the outcome of my pattern matching is two hypotheses, two assumptions. First of all, I have this assumption that P holds for n and P holds for n plus 1. And actually that's what I need because I want to prove P for n plus 1, just it's written slightly different. So again, simplify, and now I use the assumption. And that's pretty much the same because, oh no, it's not the same. This part is harder because this is n plus 2, and I have only assumptions for n and n plus 1, but I also have this this formula that for if I know this p for n and for n plus 1, then I know it for n plus 2, and this is exactly what I need. So let's apply this assumption. Okay, now it looks doable. So let's apply my inductive hypothesis. It's done. So that was the proof of this. Like my first thing in this proof, I introduced this goal x, this even stronger goal. So now this is proved. So I'm going to prove this my original goal, and that's very straightforward because this is my assumption is clearly stronger than my actual goal. So I just go with intros, and then I apply x, and I'm done. Okay, so this double induction schema is defined and proven. And now I can prove this with this great weapon that I got from solving my quest. I can attack my lemma that all odd or even. Not for all, not for number n, it's either odd or even. But first of all, I will ask for one more good weapon, and this is tactics omega. So far, the tactics we have seen so far, they are very simple. They just use some assumption or do some simple transformation. But actually, the power of Coq are some very fancy tactics, and one of them is omega. Omega is so maybe I start. There is something called Presburger arithmetics, and this is just the arithmetics without multiplication. It's just number and addition and equalities and this inequalities greater or equal. Yeah? And if you have jakiś układ równań. How do you say układ równań in English?
Equations.
Set of equations?
Yes.
Okay. So when you have set of equations without quantifiers in Presburger arithmetics, so it just constants, variables, addition, you can just use tactic omega and it's proven for you. And this tactic is, because this theory is solvable, and there is effective algorithm of proving or disproving every set of equations. And similar tactics, Coq has similar tactics for other theories like ring, and some other algebraic structures. So let's first import omega, and once we have omega, we can prove this all odd or even. So first of all, we need this double induction that we just defined. So now we have three goals. Two of them are the base steps for 0 and for 1, and there is this the base cases, and there's the step. So now we must prove that something exists, and this is constructive math. So by proving that it exists, we must provide the object. So how we provide, we guess. So what is this mysterious number m that such that 0 is m plus m, or the 0 is m plus 1? Well, I guess it's 0, and then I declare that I will prove this left part of conjunction, and then it's trivial. So that's what I do here. Now I do the same for 1. I also guess that m is 0. Okay, so easy part is done. So now I have this terrible unreadable goal. So first of all, I want to simplify it. So I say intros, and I consume this I put the assumptions on above. So now we know that n is natural number, and we have this inductive hypothesis, and we have our goal. So this inductive hypothesis is still quite difficult to read, quite unreadable. So let's pattern match. Okay. So after pattern matching, we have these two hypotheses. So we'll need only the first one. So let's get rid of the other one. And now again the pattern matching. And now it's finally quite simple. Maybe I go one step back. So here you have assumption that such number m exists that meets some property. So it's constructive math. So if Coq says that it exists, I can ask Coq, give me this number, give me this mysterious number, and this is what I'm doing by pattern matching. And so happen, this number is x. So when I have this x, I can finally guess what is my m that I am going to find. This m is x plus 1. Because this, like, you know, this induction, so it's always plus 1. So yeah, so what is happening here? I have these two equations and one hypothesis. Oh no, I have conjunction in hypothesis. So again, I do pattern matching, and now I want to know like which side of conjunction is true. But actually, this time Coq doesn't know which side is true. So what I have to do, I have to prove for both cases. Because like at this point, it's just assumption, but we don't have this proof. We have to be prepared for both eventualities. So if
What's the difference between the first and the same?
So when I prove when this alternative is my goal, then I have to find, like, I have to know which side I'm proving. But when it is an assumption, then maybe it's not decided at this point, because we're defining some general function. So, like,
Yeah, I know, but after constructing, you
Let's go
like two
one
options,
step forward.
and they look exactly the same. So.
sorry.
And one more.
This step, you mean?
Yeah.
That's a good question. Is there any difference?
Plus one.
This is plus 1, this is plus 1. No. Can you spot the difference? Maybe they're not different. No, I know. In the first case, we have assumption that n is x plus x, and in the second case, we will have assumption that n is x plus 1. Of course. Because that was the assumption that we just destructed.
Okay.
So we have, like, in these two branches of our proof, we'll have different assumptions. Okay, so if n is x plus x, then I choose to prove the left part. So how I prove it? Like, it looks that this is true, because like n is x plus x, so 2 plus x plus x is x plus 1 plus x plus 1. So let's don't do it manual, let's use omega. Ta-da! So now I have these different assumptions, so I'm going to prove the right branch. Okay, let's use omega again. It's defined. So now we are going to extract the proof. So tell me what kind of function you expect to be extracted.
Origin.
Yeah, that's the name, but what it should do?
Norm into bool should return boolean. Predicate. Any generic norm into bool.
No, actually no. Actually, this function, like, when I was at this point, I expected this function to, for every n, produce the, maybe so order even claims that there exists some m, and I expected that I'm going to see this m. that this function will produce m. So basically, it's half of the input. So when I pressed the button, I was very surprised because the program doesn't look like I wanted. It basically doesn't do anything. And unfortunately, there is good reason for that. And the reason is exactly that this odd or even is a prop, and prop is this impredicative type, and impredicative types are not extracted into programs in Coq. But don't lose your hope. Actually, we didn't exploit the impredicativism. We never exploited that. We use only induction, and induction is fully predicative. So we can just define it everything once again and prove it in predicative terms, and I'm prepared for that. I have exactly the same theorems, just here I defined, like, don't look too carefully on that. I just tell you that I defined this existential quantifier not in prop but in type. So now we have predicative existential quantifier, and I also defined conjunction and disjunction in predicative terms, and I defined some notations like these 3 pipes and 3 ampersands to name them, and this double induction is exactly the same, just instead of and we have this triple ampersand. So let's go very, very quickly because it's exactly the same. And exactly I use omega for this proof. And now we have some meaningful function. So yeah, I know this window is too small, so let's open it in some. Now it's too small, I guess.
No, it's okay.
Okay, so you see, first of all, it sorry, let me scroll. So first of all, there's some stupid comment, and then is the definition of the type of natural numbers. Here is induction schema for natural numbers. It was like happening behind the scene, but when exported to Haskell, this is also defined. And then we have definition of plus and of our existential quantifier. And we have definition of double induction. It's like totally unreadable for me. I have no idea, but it compiles. And yeah, I just to use this program, I define instance of show for my type odd or even. Like instance of show, it simply means that I define toString. I want to, we want to see the results, so I define toString. And let me compile it. So I remove this shit. Now I have this prepared, so I add some imports and so this is the toString, and this is some helper function that translates integers to these inductively defined natural numbers. Okay, it looks good. Let's save it. Do you see it? Maybe I can So this is Haskell, so GACI. Okay, it compiles. So how we use it? Let's try. That's the name of the function. Let's look for this capital O. I think it's good. Let's try for successor. It's the same. Let's try for 2. Yeah, it's 1. I think it does what we expected. So let's try. It should be 9, yes? 1, 2, 3, 4, 5, 6, 7, 8, 9. It works. Okay, that's all I prepared for today. Any questions?
So, 2 questions. Let's say you want to prove something and you have this proof in Coq. Can you like export this to white paper and show this to some other definition in the Coq?
I mean automatically?
Like, yeah.
As far as I know, no.
And the second question is, have you heard about IDE? Programming language, can you compare this to Coq somehow?
Yeah, I know Idris has these dependent types, but I don't really know much about it.
Right.
So, but this is probably kind of similar. Just the type system may be slightly different, but it's like the same ideology, the same way of thinking. Yes.
All right. So this, I would like to make sure. So this is a tool that allows you to make sure that you have a correct proof for a theorem of first order intuitionistic logic. Because for example, I noticed that you have cheated a bit in defining the predecessor, because there is no predecessor of 0 in the real, not real, but the
I mean, like,
standard arithmetic we know.
I mean, this is my definition, so like it's not.
Right. Yeah, I give that to you. But would it be easy to define, for example, an arithmetic about which you could prove that there is no predecessor of 0? Because in standard logic we would use employ instead of improving this about like normal arithmetic, we would use reduction ad absurdum, yeah, the double crossed. And this is not allowed in intuitionistic logic. This is not possible there.
No, I think it's not possible to prove that, but there is this technique. Normally when, like in intuitionistic logic, there are many propositions that you cannot prove. Like let's say that this P is a theorem of classical logic and you cannot prove it, but usually you can prove that not P whole. Not P is usually theorem of intuitionistic logic in such cases. So probably, and not P does not imply P in intuitionistic logic. So probably you can prove this double negation of.
But you can prove that there is no predecessor of 0 in intuitionistic logic, because negation you prove by proving that the sentence is implying false. You said that in a slide.
Yes.
So you can probably prove that from the fact that there is a predecessor of 0, that it implies false.
That's like using the excluded middle law that is exactly not allowed in the logic. actually common. Because you would need to provide a function that would, you would actually have to check that all functions would provide exactly what that, but you can't do that in a finite.
Okay, any more questions?
I've got a question.
Yes?
So I can easily see the usage of Coq to translate white papers into programs. So you can just automatically, if someone wants, he can take a white paper and try to prove it using the Coq. So it's one of the...
Actually, like in normal white paper, like a lot of details, it just said it's trivial or simple exercise left to reader. And the thing with Coq is that we have to prove all of them.
Yeah, but what I want to say is that someone can do that. But I wonder if there is the other side of the picture. So if the Coq was used to prove to find out something that was not already known in a white paper. So if there was any invention or anything like that with using Coq, or is it like only the...
So it's a very good question. So one theorem that was proven, one famous theorem that was proven with proof assistance is four-color theorem, and there is a proof in Coq. Think the first proof was with some other proof assistant, but I guess that's the most prominent example of actual theorem that was proven with proof assistance.
Yes, so can we get back to my original question? Is Coq proving like first order logic, first order intuitionistic logic for the... If it is,
well, this theory is called calculus of construction. It's not exactly first order.
So what's the relation of that to the classical first order logic and the intuitionistic first order logic?
Yeah, honestly, I'm not prepared to answer this question. Maybe another time.
Yeah, sure. You know, that probably will be the 10th meeting of this meetup. So.
Of course.
Can you prove that Coq is true? True. I mean.
But what do you mean by this?
This is a silly question. I mean, if you...
like automatic, like verification of the source code, for example, of Coq itself. Well, that's a very valid question. So, but even if I do this with Coq,
would you trust it?
why would I trust Coq in the first place? So I think the kernel of Coq is very small. It's very limited, so that it can be inspected by independent mathematicians and programmers, and that's the source of truth here. But actually, another practical application is that there is a C compiler. I think it's called CompCert, and it's like certified compiler. So every optimization it does is proven. I think it's proven with Coq that it doesn't change the semantics of a program. So it's compiler C to assembler with optimizations, and it's semantically proven. And one more thing about this application. So I imagine that in nearest future there will be lots of applications, because we are going like so much into Bitcoin and blockchain and smart contracts. And with smart contracts, you really want to have some level of certainty that this contract is correctly written, because like you're giving your money to this contract, and if somebody finds if there's a bug or somebody finds some way to hack the contract, he or she will take your money. So I imagine that there will be a lot of like automatically assisted certifying for smart contracts.
Theorems that you've written were basically reusing some comments over and over. So isn't this process automatable? Can you automate the process of proving the theorem?
So yes and no. Yes and no. There are some tactics called auto and intuition that try to apply other tactics and find the proof, but they are also limited. And if you have a this neither of those would prove the theorem we have proven today. So it's only for some more simple tautologies. So to some extent you can use this automatic tactics, but if you have something complex, just the space of proofs is too large.
I mean, if you have a strict conversion between one type and another type, you can guess, you can automatically prove that all values of this type are logically transitioning to that type. There is type check, right? In Haskell, a library that automatically checks, gives you opportunity to unit test anything that you've written and you don't care with. You've defined only properties of your system, and it defines automatically. It automatically checks all possible scenarios. And this is what I mean. Can you define the behavior and within this define some process of what do you expect from it? From you define lemma, you define what you expect from this.
But if I understand, you're referring to this some finite sets. So yeah, if you check for every possible combination, then probably have some finite set. So for sure, for finite set can be done. Actually, I don't know if there is, probably there is such tactic. I don't know about it, but there's plenty of tactics. And even if
depends on how much power do you have.
And even if there is none, you can define your tactics in this LTAC language. So for sure it's doable.
What actually this function in Haskell does? Because it's something
from what I recall, you define some
this function.
What if it's all other even? I would expect it to say true.
So
because all are other even, right?
So it produces objects of this type. And this odd or even type, it's, let me scroll.
I'm trying to figure it out, honestly.
Where is it? Oh, it's here. So this odd or even type, it's a type with one constructor. So it's a tuple. Basically, type with one constructor is a tuple. So it's a tuple that the first element is a nut, and the second element, this looks pretty silly in Haskell because the second element is a proof, and the prop objects were omitted, replaced with union. So it's a pair, but only first element have some actual meaning. And but originally in Coq, it was the number and the proof that this number meets the criterion.
Okay. So basically it's a number.
Yeah, in Haskell it's a number. It's a number wrapped with some tuple.
So basically in Haskell code now you are proving that any number has corresponding number.
Yeah, you can say so. And the corresponding number is
proving this with finite amount of numbers.
And then input I get numbers. For number I get different numbers. Okay.
Okay. No more questions?